So first of all, the intuition behind regularization is as follows. So remember, we want to minimize some error, some loss. So we have a classification term in general that we want to minimize, and in the case we have seen before, it's minimizing the loss. We don't want to make a lot of mistakes on the training error, right? But we're going to add to that, besides minimizing the error, adding C times some regularization term, which is actually a function of the model F. This means that, okay, we want to minimize this quantity of loss. At the same time, we want to keep the contribution of the features reasonably controlled, right? So this is just an idea. We're going to definitely see more of that in your machine learning course coming up. In the example of regression, what we can see here is that, for example, for the first model, the function of x would be just the function of a line. Would be lambda 0, and lambda 1 being parameters. Lambda 0 plus lambda 1 x is the equation of this line here. So the function for the second one would be a polynomial of degree 2. In the third one would be a higher degree polynomial. So if you want to do regularization, what we can do is to avoid high degree polynomial by setting up their weights, lambdas, to be very small by regularization. So another way to control the way we are performing on the training and test set is to use what we call a train validation test scenario. For example, you have your data set. What you can do is to split the data set into 3 pieces: the training set, the validation set, and the test set. So in this setting, for example, we could decide to split 60% for learning the model, 20% for validation of the model, and 20% for testing the model. So the test set is just like a data set that we don't touch at all. You put it in the drawer, you don't look at it, you build your model, you try to find your best parameters. Once you are final with your model, you just apply it on the test set. Okay, so first step is training set is the set of examples used for learning the model. Example, a classification model. So you use the example that you have in a data set to build the function f. The validation set is a set of examples that cannot be used for learning, right? But that can help you tune the parameters. For example, in the case of k-nearest neighbors, you need to know what's k. K will depend a lot on the domain that you are working with. So if you want to learn k, you could use some validation to try different k's and see which one would do the best, do the best performance, have the best performance. Finally, the test set is used to assess the performance of the model and provide an estimation of the test error. This is the out-of-sample error. Note that you should never use a test set in any way, right, to further tune the parameters or revise the model. This means that given the training and validation set, do whatever you can to build the best possible models, tune the parameters to derive this best possible model. Once you get this model, call it F, right? Apply it on the test set, but never revise your model based on the test set. Your out-of-sample error should be a true out-of-sample error. So you could revise, otherwise you're going to, again, try to overfeed the test set, etc., etc. So in this scenario, just keep the test set separate, always separate from your learning step. Another method for estimating test error using only training data is called k-fault cross-validation. In k-fault cross-validation, you're going to use the training and validation data to squeeze as much as possible out of your data. So given the learning algorithm A and given a data set D, you're going to first start by splitting your data into k partitions. So you split your data into k equal partition. So typically what you do is you take your train and validation set and you split it into k pieces, right? So the first round you would do the training on the first pieces, right, first partitions, and then do the testing on the remainder partition. So that would be the test. The next stage, you will you will actually use 4 other partitions, which could be this partition here, and here, and here, and here, and afterwards do the test on the remainder partition. And you would do this 5 times if you have k equal to 5. All right? So the idea is that you're going to look at the data and squeeze it in different ways. And the average, you calculate then the average error, which is over all the faults, which is the error done on each of the partitions dj. So this gives you a better assessment by looking at the data and squeezing as much information as possible out of it. So suppose we went through all that process of finding the best model. We try to be careful that the model is not overfitting or underfitting the data. So how can we assess quantitatively how our model or function f is doing? Typically what we want to do is to calculate the number of errors that the classifier is doing. In which case, we're going to draw what we call a confusion matrix. A confusion matrix is a matrix of numbers that are actually that actually quantify how we are doing. So in a confusion matrix, what you're going to contrast is the actual label versus the predicted label. So the actual label is the label that comes in your data set that tells you whether the example is positive, negative, banana or apple. The predicted label is the label that you obtain by actually applying the model f. We're doing f of what? Of xi, right? So you have an instance xi or an example xi. You apply the model f and you get some predicted label y hat. Okay, great. So in this table, what we're going to assess is how many errors you make. And as you may guess, the errors actually are in this section here and in this section here. So if your example was positive and you predict it as positive, great, you make a good prediction. And you add this number to the number of true positives that you are making. If your label is negative and your model f is predicting it as negative, very good job too. You are creating a true negative, which means you made a good prediction on a negative example. However, if your example was positive and you predicted as negative, you made a mistake, right? And you're going to increase the number of false negative in your table. If your label is negative and you predict it as positive, it's also another kind of mistakes. Kinds of errors that we can make are errors that are either false negative or false positive. Based on the confusion matrix, we can calculate different metrics that tell us how our classifier is doing. So there are different metrics you could use. You could calculate something called accuracy, which is the percentage of predictions that are correct, right? The precision, which is the percentage of positive predictions that are correct. Also what we call recall or sensitivity, which is the percentage of positive cases that were predicted as positive, or specificity, which is the percentage of negative cases that were predicted as negative. Depending on the application, we want to see all kinds of errors and estimate how many errors we are making on the positive, on the negative, and how this compares to each other. Okay, great. So an example of that is that in medicine, for example, we like to talk about sensitivity and specificity in some cases where we want to see, for example, whether we predicted the disease correctly or predicted the disease incorrectly. Okay, so after going through that, let's finally review the terminology seen today and the concepts that we have learned. So first of all, we call an instance or example is data point in the space. It's a line in the row of our fruit table, for example. We talk about feature, which is a variable or description of the feature. It could be the weight, the length of each example or each instance. We talked also about label, which is the tag that we provided to each example. The example is either a banana or an orange. We talk about supervised learning, in which we leverage both the feature values and the label, and supervised learning, in which we don't expect to have labels. We spoke about classification, which is telling whether it's a banana or an orange. Our regression, whether what would be the weight in function of the length. We spoke about clustering, which is how to put the data together by finding clusters. We spoke about prediction. Whenever you build the classification model, it's possible to use it to make a prediction on an unseen example. We spoke about training set. This is what we use in general to derive your model. We spoke about validation set, which is a set not used for training, but used to find the best parameters. We spoke about test set, which is the no-touch data set. This set is something that you put on the side, you don't look at all during the learning time. You just put it whenever you want to assess how your function is doing or your model is doing on an unseen data set. So this is helps you estimate your out-of-sample error. We spoke about k-fold validation, which is a different way to slice and dice your data set so as you get the best performing model with the best performing parameters. We spoke about classification error, which is how much error you're making in predicting positive and negative example. We also spoke about loss function, which is a way to assess the classification error. Two important concepts we have also seen is overfitting and underfitting. When you find a model, we try to find the best suit model, in which we actually don't underfit the data by finding a very, very, very simplistic model that will make a lot of mistake, or finding a very, very, very complicated model that will actually also make lots of mistakes. That would be overfitting and underfitting. And finally, we spoke about regularization, which is just, I gave you just an intuition of that, which actually aims to use all the features to find your model, but then you could just temper a little bit and control how the features contribute to the final model. So I think this was our initial, our basic concepts on what's machine learning. Basically, you will definitely see way more information in the next couple lectures, but also you're going to take a class on machine learning in this series. Finally, I would like to mention some machine learning resources and books. So for example, if you want to have access to introductory textbooks, I would recommend the book by Tom Mitchell and Abu Mustafa, who actually provide a very understandable introduction and several methodologies of machine learning. If you want to dive more, I would recommend this last three books. The Element of Statistical Learning, that has the statistical side, an introduction to machine learning part. And also, I would recommend Pattern Recognition and Machine Learning from Christopher Bishop, and Pattern Classification, which is a classic book in pattern classification, in which you'll find things like k-nearest neighbors and all its variants and so on and so forth. There are also a wealth of resources online, and this include all major journals and conferences such as ICML, NIPS. These are the top one, pretty much the top one conferences in machine learning and AI. You could have access also to a large number of video lectures in this website. Also, if you are more interested in the machine learning, the theory aspect of machine learning, I would recommend checking this website here. There are other groups and newsletters that you could also tap into that has a wealth, again, of information about machine learning. So thank you again for your attention in this lecture. Next time we are going to talk more about linear models and also nonlinear models. So stay tuned. See you next time.